All right, we start. I call these 5 lectures that I will give you in these 5 days, basic notions of statistical mechanics. As you know, it's a part of the course Statistical Physics with Python. And let me ask you just, all of you, I see, had graduated in mathematics, physics, probably I hope that you had some basic exposure to statistics and probability theory. But what do you expect to learn in a course of statistical mechanics or statistical physics? You can reply, for instance. Let me go. Okay, Anna, that's your name came first.
Yes. We would probably be studying the distributions, different distributions, maybe taking it a step further because that's what we did in our bachelor's. And with Python, I guess we would be problem solving using programming instead of just doing it all with pen and paper. So.
All right, thank you. Anyone else would tell me what you expect of a course in statistical physics? Idris, what do you expect of a course in statistical physics, and what do you think is the subject of statistical physics?
How particles behave in a set of large numbers.
Of large numbers?
Yeah, I mean large numbers of particles.
Okay. Boris?
I think you are on Boltzmann. Yeah, Boltzmann. I forget the.
Dirac.
Yeah.
All right, Saeed.
Your question is what we want to learn.
What do you expect to learn in the course of statistical physics?
Of course. There is some more very important things that I planned for many years to learn them. But for now, I missed its name. But partially I can't describe to throwing pebbles in a circle. And it was the name of one of cities in France.
Monte Carlo.
Yeah, right. Thank you. Monte Carlo and Markov chain. I think these are very important for us, for our future works. And I like to learn how to do them in Python.
All right. Thank you, Saeed. Thank you. Dionys, would you share your?
I think I expect to learn, similar to what Amna said, to be more familiar on, or to have the intuition on when to use the different distributions for a given system, or to be more the mastery of using the different.
Tyrell?
Yeah, I also am expecting for much more on the probability, the applications of the probability theories, and some statistical inference that we can have.
Okay. So did Anna respond? Only Anna has remained, right?
No, I've responded.
Not higher, Anna.
Anna.
Oh, Anna.
Okay. More than mathematics, I will expect how to analyze systems and how to apply those mathematics to that systems, and interpret all the values that we can obtain from mathematics. More than.
Okay. All right. Thank you. All right. So, well, in principle, I hope the whole course, the 3 parts, the 3 modules of the course will sort of answer your questions, which you put for yourself studying statistical physics. In these 5 days, actually, I will not tell you about, for instance, Bose condensate. That probably is a topic more advanced than we could cover in 5 days. But I just wanted to refresh, to review, or let's say to consolidate. I'm trying to consolidate your knowledge, which you have about statistics, physics, and well, if you missing some concepts, hopefully you will learn it in these 5 days. Learn these concepts. All right. Well, historically, I must say that statistical physics was developed in an attempt to explain the origin of physical laws described by thermodynamics, hydrodynamics, and similar disciplines, successful disciplines, but these disciplines operate at large, as we say, macroscopic scales. The question then comes, since everyone knows today that matter consists of molecules, you know, atoms, tiny particles invisible to us, how these laws of thermodynamics, which quite simple, or hydrodynamics, which describe motion, collective motion of many particles, how do they emerge? That was originally the problems that motivated the development of statistical physics. And by the way, the very fact that matter consists of molecules and atoms, it was proven with the help of developments, with the help of theory of statistical physics. And in the time when Boltzmann wrote his first papers on the subject, it was pretty much debated if the molecules existed. There were advocates of continuous theories of matter, that matter consisted of some, you know, continuum material. Regardless of the origin and motivation behind the statistical physics, in the context of statistical mechanics, scientists developed a very successful approach that can be applied more generally. I know that many of you studied finances or some sciences that are not directly related to physical matter. So you could already encounter that methods of statistical physics or similar concepts applied also there. And today, this approach of statistical physics addresses various questions in economy, finances, information theory, ecology, neuroscience, many fields, biology in general. And because you are pursuing the diploma program in quantitative life sciences, that is going to be, yes, I see, thank you, Ivana has joined us. Yeah, so while you are studying the theory of the quantitative life sciences, of course, you will use a lot of methods that appeared first to study particles. Yeah, probably all of you, all of us, even me, when we studied basic arithmetics, we used fingers, right? You know, just analogy. So first we learn how to count fingers, items, and then we kind of generalize these concepts. Now we can count money, count liters of matter, and so on. All of you probably pass the same sequence in your acquiring your arithmetic skills, right? And in a similar matter, when I will talk about particles, molecules, you actually may think that it's like fingers for arithmetics. Many of these tricks, theoretical concepts and ideas, they can be applied not only to study particles, all right? So in 5 lectures, I'm actually trying to introduce you to these concepts of statistical physics that can be applied more broadly than just studying particles of physical particles, okay? Do you have any questions about this? All right, write me in the chat if anything, and if no one has questions, let's continue. So statistical mechanics, there are two parts in the word, okay? Statistical. What do you think is the purpose of statistics? Why do we need statistics to study physics? Can anyone suggest his own idea about it? Someone has thought of why do we need statistics?
I think it's for making a prediction.
Okay, so for instance, we have we have Newtonian mechanics to make predictions, and we don't need statistics. So why suddenly there is an interest for statistics to make predictions?
Study a large number of a system with large number of particles or another system.
Okay, so there is a large system with large number of particles, and what was the difficulty with such systems? Why would you like to apply
to map each particles, each unique particle? So instead of that, it is better to see the collective behavior of them.
All right, I understand. So it's easier, right? So it's easier to describe everything. Would be nice to describe everything together rather than to describe a large number of particles, which probably impossible.
There's too much information.
Too much information. Yeah, there is even
for microscopic states. Hence, we need macroscope. Hence, we need to we need stats to analyze it as a whole.
Yes, that's, by the way, there is maybe you have heard this word reductionism. So when you try to reduce description of your system to as less information as possible. That is right. That is one of interesting fact. But the problem is, okay, that when the system contains so many particles, it's unfeasible to describe all of them. And yet sometimes we succeed.
It's also about prediction. So if we want a predictive model, you have to use statistics so that you know exactly, you know, which percentile, what result lies in, etc., etc. Okay. I mean, even in the social sciences, we use probability and statistics because there are so many outcomes.
Yes, many outcomes.
Yes,
that's
emergent property.
Again?
Is it about emergent properties?
Emergent properties. Well, yes, but I think that yes, there is such thing as emergent properties. Probably this is not the first thing that came to my mind if someone asked me. But yes, I think now this theory of emergent processes, this is a rather concept, and that was born already in statistical physics. But yeah, okay. Other ideas? But okay, so why statistics, right? Okay, let me give you just example. A game of coin, right? Everyone sees my coin. By the way, yes, you see the coin, right? The coin game. Okay, I just throw the coin, then whatever is the heads or tails, you try to guess what will be the outcome of this experiment. I throw coin and look, is it heads or tails? All right, in principle, what prevents us to apply, for instance, I will measure mass distribution in this coin and try to apply classical Newtonian physics to predict classical mechanics to predict the outcome of these experiments. What would be the problem of such approach? Idris?
You can't predict the result.
What?
You can't predict the result of flipping a coin with the classical mechanics.
Why? What happens?
The problem of initial conditions.
Oh, that's good. That's good. Right. initial conditions. What else?
Chaos.
Chaos?
Yeah, I mean, anything can, any small change can
Yes, good. I understand.
result in the outcome.
All right. All right. Yes, right. So everything like this, we could say, okay.
It's also what result we want, right? What are we measuring? Does that match the technique we're using? Like using a mass distribution to find the outcome of heads or tails is like,
yes. So
it's like,
thank you. Yeah, that is right. So one word which explains what is the problem is the uncertainty. All right. There is uncertainty in the conditions. Like the initial conditions is one uncertainty. I don't know where I start, right? Maybe it was up, heads or tails up when I started, right? And if I can predict the outcome of experiment when the coin is heads up, is one outcome. But if I repeat experiments, but my coin was turned tails up, probably the prediction would fail. Other thing, I cannot, there is a protocol, right, which I follow. I cannot throw the coin all the time with the same force. Maybe one time I throw it a bit stronger, another time weaker. Uncertainty, right? Another point of uncertainty is that such calculation would be utterly useless because, for instance, if I take another coin, right, as we often do, all this prediction may fail. So it's a question also, what do you want to, what kind of answer you, what kind of problem you're trying to say, you're trying to answer. So often in physics, we have this problem. We want to make some predictions, but our information about the system is incomplete. Who knows another reason for uncertainty in physics?
Uncertainty principle, like
No, yes, quantum physics. In quantum physics, there is a whole, so nature of uncertainty in problems that we face as physicists can be really different. But what is common is there is some uncertainty. You do not have all information about the system. Someone asks you a question as a physicist, and you are a poor physicist, have to give him the most sensible answer that you can get, right? And statistics and probability theory are mathematical disciplines, okay? These theories, they mathematically describe uncertainty. That's why we need it as physicists as a formal language, which we use to describe uncertainty. We can use statistics to describe uncertainty of initial conditions, and we can give an answer and say, look, yes, and apart from uncertainty, you have the many-body problem, which has not yet been solved. Many-body of, you mean in quantum physics, or we have many-body problems, yeah, but phenomenon is quantum. Chaos, there is a lot, nature of uncertainty, I repeat, can be different. And physics is one, but when we come to economics, the nature of uncertainty becomes even more difficult to formulate, okay? Anyway, there is theory of statistics and probability, and that's why we need it in physical problems. It's a language, mathematical language, which helps us formalize, formally state what is the uncertainty in the problem, and to explain what is the uncertainty of final answer. So we solve the problem, we say we solved the problem, but the outcome of this experiment with coin, for instance, will be uncertain. And you give also quantification of how uncertain it will be. And everything like this can be expressed using language of statistics and probability theory. Even quantum world, which is so weird and has this weird nature of uncertainty, still we can use statistics and probability theory to apply logic, to mathematical logic, formal logic, to solve problems. Okay, now what about mechanics? So why comes mechanics? what do we try to do with mechanics? Okay. All right, well, that's pretty simple. In the times of when the theory was developed, there was an attempt to explain thermodynamics and hydrodynamics as a motion of particles. And in classical mechanics, the word mechanics would of course mean the dynamics of these particles that follow laws of motion, Newtonian, Hamiltonian, quantum laws of motion, okay? But in principle today we can consider general dynamical systems which are not quantum, which are not Hamiltonian. Did someone want to say something? Okay. Do you have any questions so far? Okay. So let's see, for instance, dynamics can be really general. So dynamics can be stochastic, for instance, when there is no law of motion, which says that if you find your particle here, then in 5 seconds it will be there, as for instance, classical laws of mechanics would tell you. Let me consider this dynamics, okay? This is dynamics, so this is cartoon or egg carton, so there were eggs sold before. And then I take, let's say, 2 coins. Let me take, okay, let me take 2 coins, okay? And the dynamics will be discrete time. What do I mean by that? So that you will observe the system as a sequence of frames. So I show you the system right now. Okay, hopefully it will work. Okay, you see coins here. Okay, then at my whim, I shuffle it, and the next frame you see is this one. Okay, and absolutely arbitrary. So you have no information of what is going on in my head and why I'm going to what will happen in the next frame. You will see these states of the systems. Instead of continuous time, there is a sequence of frames. Okay, that's why I told a discrete sequence. And note that coins now are absolutely, say, indistinguishable. So we have this system of, so let me put here a cartoon, sorry. So we can introduce a system of coordinates. Let's say I call this x, coordinate x, which is discrete, right? 1, 2, 3. And there is also y vertically, which is 1 and 2. Okay, possible coordinates here in the whiteboard, you can see. Now, I say we have 2 coins, so for instance, I can put here 2 coins, all right? And tell me, with this information that you have, so practically you just have that each time you see this cartoon, particles just moved without any reason, without any law. What is probability of finding this particular picture that I draw? Okay. Let me give you just 3 minutes to think about it. Just in case someone has, we can discuss this problem. So who has an idea how to approach this problem?
So it is possible to have both particles in the same
no, yes, yes, sorry, that's important, right? Only one particle at a time can occupy the cell, okay? This is important, thank you. So who has ideas? Let's just a little brainstorm. You already started writing something, but okay, Who has idea? Just come up, speak up.
And for me, if it's a one particle, the probability to find the particle in one cell is 1/6.
1/6.
Yeah.
Okay.
Since we have two particles and both, if the first took one cell, they give the condition to the second cell. That means to the second particle. That means the probability to find the second one is 5/6. That means the probability to get both in the whole of the cell is 1/6 times 5/6.
Okay, let's see. So how do we define probability? Okay, so this system has, how we describe, yeah, there are like coordinates, but that does not matter. So we can count all possible configurations in the system. There are just 6 cells, two particles. And what can you say about each individual configuration? What is probability relative to the others? I can't hear if someone speaking. Is someone? No. Okay, we
said two particles can't occupy the same cell.
So 2 particles cannot be in the same box. Yes.
Okay, so
they cannot.
One of particles will be with the probability of 1/6, and fortunately the other will be with 1/5. Because
can you write in the chat what you say? So probability of particular configuration. All right. All right. Let's first of all. Okay. Just let me draw 2 such possible configurations. Okay. Tell me which configuration is more likely. Let me call this configuration A and configuration B.
They are the same.
What?
They have the same probability.
Exactly. Equally likely. Yes, of course. Right. You have absolutely no information except that it changes. So any particular with information that you have, which is known, you can only assume that all of these configurations are equally likely. All right?
Sir, I would like to add something. Since the position is important, that means we can add a combination to set all the possibility multiplied by the probability 1/13.
I just have to add that since this will be an expectation value because it's a discrete set, so the method will be different.
What would be different?
Like the expectation value, x into probability of x.
No, I'm not asking you about x or y. I'm asking about probability to find these particular values of x and y for 2 particles. Okay, but in principle, that can be distracting for you. Let's say, yeah. Let me put it. So let me just erase x and y. So I just say, yeah.
Is it just that image A or the condition of being diagonal? Because if it is just only that picture, it will be 1 over all the combinations.
Exactly. So it will be 1 over all the combinations. So as we figured out together, any configuration which you see is equally likely. Okay, equally likely, any configuration. The configuration that I call A and the configuration that I call B, they are just equally likely. Okay. So now the probability is just the total number, or so it's, since they're all equal, it's 1 over total number of configurations. Let me call it W.
W, yeah.
Right?
Mm-hmm.
So that probability summed, okay,
Is one.
Is one, right? It's normalized. Now the question is, how do we compute probability given that particles are indistinguishable? So that, in other words, if I swap these two particles, nothing changes. Does anyone remember what is the law that governs this problem?
Bose-Einstein?
No, Bose-Einstein.
No.
So it's combinatorics problem. It's a famous combinatorics problem, and probably someone can come up, recall a name that it has.
These are permutations and combinations. So,
Well, correct about permutations and combinations. So there is a very famous word. So it's okay. Let me call. Yeah.
Give me a minute. It's coming back to me.
So we have, let's say, n particles. No, yeah, n particles and no, n states. So we can number here in this problem each cell. Okay, there are 6 of them. So 1, 2, 3, 4, 5, 6. Okay, n equals 6, and we have 2 particles. Okay, and what we do actually, we just draw 2 items from a collection of 6 items. There are 6 cells which we can number, and we just randomly draw 2 of them. This is called sometimes binomial coefficient. So I think this is, no, sorry. It's probably, I always forget the order in which they...
It's NCR.
NCR. We have K, no R. So
K?
it's,
okay.
Yeah.
Well, yeah.
So,
K.
which you can read actually N choose K.
Mm-hmm.
Okay, choose K. Okay, and now you can look up if you have not encountered in your curriculum derivation of this number. This is just n factorial divided
minus K
by K factorial
into n minus K.
N minus K factorial. So actually someone already came to a very close number. I see either is has written an estimate.
Yeah,
So,
I forgot to divide by 2 because the particle.
That's it. And it's actually a very important observation, because if the particles were distinguishable, so if we consider something like that, the number would be closer to 30.
Yeah.
But we have to divide the total number of combinations by the number of permutations when we can swap the particles. And this is the factorial. Yes.
Yeah, the K factor.
Okay. Yeah. So who knows? So who can evaluate this number?
15.
15. Yes. So the probability of each state is 1/15. All right. And to describe this simple system, this really silly system, we just need to specify in which cell each of the 2 particles stays. And there are at all just 15 possibilities that we can describe. In physics, we would call this one particular configuration, who knows how? Microstate. So it is microscopic configuration. Why micro comes, the idea why we call it micro hopefully comes now. Now I tell you that, so I do this experiment, which I described to you. I will just shuffle particles, so coins in my box. And then I will not show you the box, but I will tell you the Manhattan distance between the two particles. Who knows what is Manhattan distance?
The straight line distance of between the coins.
Yes. So the story goes that because Manhattan in New York is a district, a borough of the city that has parallel and perpendicular streets, and therefore when a taxi driver computes the fare, calculates the fare, he calculates the distance which he would go in straight parallel and perpendicular lines. So let me.
So basically the displacement.
Yeah, so displacement, but which is going like that or like that. So there are no displacement like this, okay? Diagonal displacements are not allowed, okay? Yeah, and in essence, if we introduce our system of coordinates, which I have eliminated, okay, so there is x, which goes like that, 1, 2, 3, and there is y that goes like that, 1, 2, okay. So who can present me a formula if I give you, so x, I, so there are two particles, I don't need I, so let me, so I give you the x of first particles, the first particle, and y of the first particle, and then I give you x of the second and y of the second particle. How do you calculate the Manhattan distance? Write in the chat. Okay, someone. Some ideas. Who has an idea how to calculate this? Okay, Aya, how do you do it?
It would simply be, you know, how we calculate the modulus, the x minus x1 minus x2.
Yes,
plus
y minus y, taken in each difference taken in the modulus. So so Manhattan distance is x1 minus x2 plus y1 minus y2. Okay. All right. Let's say, Boris, what is the distance between these particles? Manhattan distance.
It is 1.
1. Okay. Said, what is the distance between these two particles? Manhattan distance.
3.
Why?
When we're starting from this you are pointing on, we need to go one up and another to right to achieve, so it becomes 2, excuse me.
Okay, 2, correctly, good. So the distance is 2. What is the maximum distance that we can, what is the minimum and maximum distances that we can have in this system?
At least there are 2, and maximum, I think it would be about 5 or 6. The 1,
5 or 6,
2, 3, 4. No, 4.
No. Okay, Dionys, can you tell me, what do you think? What is the minimum and maximum?
I think the minimum is 1.
All right, because the particles cannot sit together in the same cell. Minimum can be 1. Yeah.
Maximum is 3.
3. Okay, yeah. When you put them in the corners, probably that's as far as you can go, and it will be, for instance, 1, 2, 3. All right. So now, when I tell you in this game, this system, I would be able to look in the box, but you would not be able. I would give you only current Manhattan distance m. Then there would exist many microstates, right? You can find many configurations of the systems where Manhattan distance equals 1, for instance. And therefore, historically, this is called macrostate. So I would say that Manhattan distance equals 1 is a macrostate, which can be realized by many, possibly many microstates, okay? For instance, tell me how many, what is the, so then, all right, what is the probability? I give you a problem now. What is the probability to find the system Manhattan distance, sorry, 3, yeah. Think a little bit about this and write your answer in the chat, okay? I will give you.
Are they still indistinguishable?
Yes, indistinguishable, same system, indistinguishable particles, and yes, they cannot sit in the same cell. Sorry, unfortunately, this chat does not show me that. Ah, yes, there is a time. Yeah. Okay, Danessa thinks 2/15, 2/15. Okay.
There are two possible configurations of two Manhattan.
Yes, yes, yes. Very good. You got it. You got it. Okay. Indeed, there are just two combinations. So the particles could sit here, or let me put it open, could sit here. There are just no other ways we can observe anything else. Okay. Yes.
I think we can have 4 combinations. We have the horizontal line twice.
What we can have?
I say we can have in horizontal lines. That means 1, 1 and 1, 0 and 3, 0.
Okay, so okay, so you think that we can have 9 configurations with distance 3?
5. I think, yeah.
5 configurations with distance 3. All right.
Let's say 4.
4 configurations. Yeah. Okay. Let me then try to. Okay. So let's go like that. We put over here numbers. Okay. 1, 2, 3, 4, 5, 6. For a moment, just let's number them. And so you say you have 4 configurations that give me Manhattan distance 3. First configuration, where I put my particle?
1, 3.
Okay. So particle 1 goes into 1. Particle 2 goes into 3.
Yeah.
So it's like that?
Yes, sir. Yes, sir.
And you say it's a distance. So if I now go to these coordinates, can you say me that it's confirmed to me that you think it's distance 3?
Yeah.
Okay. So what is the x coordinate? What is the coordinate x of the first particle in this?
Is it 1, 1?
No, coordinates. Okay, x, y.
X is 1 and y is 0.
Y 0? Where do you find 0? We had y1.
No.
2, 1, 2, 3. Okay.
Is it?
X, coordinate x can be 1, 2, 3. Coordinate 1 can be 1, 2. 0 is not there. Okay.
Yeah, 1, 1. Yes.
So
1,
particle
1.
that sits here, 1, 1. Okay. Then particle that sits here.
3,
What's
3.
what?
1, 1, 3, 3.
3, 3.
3, not 3, 1. Yeah.
So 3, 1. Okay. Now let's compute Manhattan distance. So how do we compute Manhattan distance? X1 minus X2 equals 2 with the absolute value. Y1 minus Y2 equals
0.
So do we have Manhattan distance equal?
No, equals 2.
Right, not 3.
Yeah.
All
I
right.
think that, it's better not to calculate that. Is, I mean, let me annotate thing. If you have a particle here, the Manhattan distance for getting in this place should be 1, then 2, then 3. That the amount of places that you have to go to the other part.
Yes, yes, that's a physical, I would say, interpretation of Manhattan distance, right? This is something that we can formally, here we have a formalization in terms of coordinates in formal mathematical language, x1, x and y coordinates, but what Anna suggested is just a very conspicuous illustration, physical interpretation, okay? All right, so that will be your homework. You will calculate all the probabilities. So I will need to know the probability that Manhattan distance equal, no, probability of Manhattan distance equal 3, we will get at home for tomorrow. Please compute me these values. Okay, probability. And what is the probability of observing a Manhattan distance 3? Who tells me? Kyrell.
2/15.
2/15, right? So it's, so how do you calculate it, Kyrell?
Because we already told a while ago that there are only 2 configurations for which the Manhattan distance is 3. And we also counted or calculated a while ago that the total number of configurations is 15.
All right. And then probability of macrostate equals, so the microstates that, okay, that M equals 3 divided by total number of microstates, okay? Just equals 1, 2, 3, okay? Yeah, right? So we had 2 divided by 15, so 2 15s. Now, for your homework, you can do homework on a paper and send me a photo of your paperwork, okay? Yeah, by email, please. Yeah, it's, I think, a simple problem that you can do by tomorrow. All right, so we have considered microstates and macrostates. And now that was a discrete system, okay? But suppose we will
Excuse me.
Yes?
Could you please review how you crossed from the microstates to macrostates?
Okay, so a microstate is any given configuration. So when particle is here, okay, and here, it's one microstate. There is only one such state that you can find in this system. But then I can consider another microstate where particle is here and here. Okay, those are microstates. Okay, and then I told you that you actually don't know what is the particular microstates, but I would tell you the Manhattan distance, and you can see that distance between these particles is equal to, okay, and the distance between these particles also equals 2. And there are no other microstates in which you can find distance equal to, sorry, 3. So yes, right? Then I say that these two microstates compose one macrostate. So when I see that, when I tell you that the system is, or you observe a system to have distance 3, Manhattan distance 3, but you don't know what is microscopic realization, that's, then a physicist say that I know that my system is a macrostate. Okay? Is it clear?
Okay, thank you. Yeah, that's
okay.
Clear.
And then there will be other macrostates, right? There will be macrostate with the distance equal 2. There will be actually more than 2 such states, and with the distance 1. And then there will be no other macrostates. And often in physics, actually, we do not have information about configuration, or we don't just want to know it at all. Like we don't want to know, for instance, positions and velocities of Avogadro number of molecules in a mole of gas. But we may be interested to know if the total energy of this mole of gas is 3 joules or 0.1 joule, right? And this measure would be a macrostate, which could correspond to many microstates, all right? And now we may turn to the continuous. So suppose that we had this little cartoon eggs, and now it's not just cartoon eggs, but I will put there more cells, okay? So I can a little bit zoom into, and then I could a little zoom more and do it infinitely many times, so that finally I would have at each point here, I could invisibly, but I would have a little cell there, okay? Question? Who has a question? I heard the voice, but I did not understand who was trying to ask something.
Oh, sir.
No. Okay. And now, yes, good.
So for the Manhattan distance, in the first part of the lecture, we didn't calculate the possible Manhattan distance. We calculated the possible configuration of two coins.
Yes.
Okay. So now I calculated the possible configuration of Manhattan distance of 1, 2, and 3, and I didn't find the 15.
Well, that's an interesting question. So often happens in physics that you know that the answer must be, for instance, you must count what 15 configurations, but you don't count. Conclusion?
No,
you did something wrong, actually.
No, it's not about something wrong. I mean, I can understand why I didn't find 15, because, for instance, for Manhattan 2, okay, we suppose there is particle in 1 and the particle in 5, and there are 2 ways to get the Manhattan distance equal to. Either we go by the axis, or we start by X and go down to Y, or we go down to Y and then we go right towards.
So you say there are only 2 configurations for Manhattan distance equal to.
Yeah.
That's what you said. Okay. Let's see how this comes about. Okay. Okay. Give me first configuration. Okay, when Manhattan distance equals to first configuration.
Yeah. Okay, so particle in one and particle in for Manhattan distance equal to, there are okay, there are 4 possible configurations.
4 possible configurations.
Yeah.
I think you're missing something.
Okay, so particle in 3.
Okay, 1 and 3. Okay.
Or 1 and 5.
1 and 5. Okay. Okay. Let me put cross. That's all what you can do?
The other 2 configurations are particle in 2.
Particle in 2. Let me put triangle and
particle in 1.
In 1.
No, particle in 4.
1, 2, 3, 4. Okay.
And particle in 6.
In 6. Okay. Square.
So there are 4 possible configurations for Manhattan distance equal to 2.
Who has more?
I got 6.
You got 6. How?
I don't know how to write.
Well, I can tell that 4 is not correct, and there should be more. I will tomorrow we will discuss this. I can show you my way to enumerate states. Let's do like that. Just sit on that. But you see, that's actually where theory helps to guide you. So you understand that there should be 15 possible configurations. That's good. That is right, because probability of any particular state should sum up. You understand it theoretically, right?
Yeah.
There can be no other way it would go, because each microstate corresponds to some macrostates. Then you turn out that you did not count all 15.
Yeah.
And you intuitively already understand that something did go wrong. So the problem is to find a good approach to calculate the states. That's what you are working on. Okay. Very good. All right, so we'll discuss this problem next time, but now I just, so to speak, introduced you to a continuous. When there is a small infinitesimal cell of size dx dy at each point on of this box, okay? Now we cannot anymore use coordinates in discrete. So before it was 1, 2, 3. Now now the coordinate will be a continuous, and just for simplicity, let's say that this is a length of this thing is L centimeters, for instance, and then we can define the coordinate x as some number nu of times L. Okay, so it's a fraction of the whole length of L. Okay, and suppose, so we can just speak of coordinate nu, and nu will be between 0 and 1. Okay, is it clear how this comes about? And so we do also, yeah, let's assume that now it's not really the cartoon, but something that is, it's now a square. We just stretched also a little bit our cartoon, and coordinate y now continuous, also runs from 0 to 1. And just before we considered that particles could not sit in the same cell, but since they're already so close, we will allow them to sit together in the same cell. That's already not important for us, but okay, still indistinguishable. So still a particle sitting in this little point and a particle sitting in this little point, we can swap them, but the configuration would be for us the same. All right. Okay, let me just try to see how you remember probability theory. What is the, so again, so basically now when I introduced this number nu, we just basically can forget about L whatsoever. Okay. And yeah, so so it's from 0 to 1, just from 0 to 1, okay. 1, 1, 0. And this is X, this is Y, okay. Now I'm asking you a question. Who knows what is the probability density of a distribution when particle can sit anywhere? One particle, I'm asking, what is the probability distribution, what is probability density of finding particle here, right? Just one particle. Do you know the name of this probability distribution? All right, let me say, this is a square of size delta x and delta y, okay? What is the probability that a particle sits here, given that particle can sit anywhere, in principle?
Delta x, delta y.
Hmm?
It is delta x, delta y.
So probability is delta x, delta y, delta y, okay? How do you calculate it?
So we have the whole surface is 1 by 1, which is equal to 1.
Okay.
And the particle must be somewhere.
Okay.
The dimension of delta x, delta y divided by 1.
Okay.
The whole space.
Yes, so we should introduce.
Is this a particle in a well situation?
No, no, well, just square. I just drop, you know, I drop a pen somewhere randomly.
It's supposed to be the Gaussian distribution. Like
why Gaussian? Why do you think it should be Gaussian?
Because it has to be normalized. So it's the normal distribution.
So, so you say that
but if the probability is either 0 or 1, then it's the binomial distribution, which is a special case of the Gaussian distribution.
So you say that probability must be normalized. That is good. Is it only for Gaussian distribution that it must be normalized?
No.
No. So argument.
So that's what I'm saying, that if there are only two possibilities, that either the probability is 0 or 1 of finding a particle.
Okay, hi.
Right,
let me interrupt you. Yeah. So so suppose we speak of probability of finding a particle. Okay. So probability density. Okay. What is probability density? It is a thing that multiplied by area, very small area, infinitesimal area. Here was finite delta x, delta y, but suppose it's infinitesimal. I hope you know the concept. Okay, delta really tiny, that I cannot even write so tiny. That gives you the probability, let me put it with capital, that particle sits there, okay? Now, I say that particle can be anywhere, okay? Which means that probability, just like before, any configuration was possible. Now, probability of x equals 0.5, for instance, and y equals 0.5 should be equal to any other value of p, for instance, should be equal, strange, I cannot move. Okay, so it should be equal to whatever px y you desire, okay? Or, sorry, yeah, that was not what I intended. So px equals 0.1, for instance, and y equals 0.33. So any point has equal probability density, okay? How now, can you find the expression, general expression for this probability density?
It's the integration of dx dy.
So integration would already, so it's a density, so it's not probability, is how much probability per unit area, okay? This is density. And probability with the P capital, I emphasize it by this line under, that would be an integration. Okay, but probability density, what is it for this problem if...
So it would be probability of x, comma y. I think I should just, I don't think I can.
Sit down and think.
I don't think I can, no, I don't think I can type it in the chat. So if we say that, if we give it a function, like a function of x, let's say, then the integration would be from whatever our numbers are, let's say 0 and 1.
Okay.
F of x and
so
y.
First of all, since it is everywhere equal, we can say that it's equal to a constant, okay? It's constant everywhere, right? So if pxy equals to whatever other pxy inside the square, so it's everywhere equal, okay? Now, how to find this constant, this constant c?
The square is x times y over 1.
X times. So formulate it mathematically. Can you formulate how would you find this c? What is the condition you want the c to satisfy? So to find c, what means? You want to find a relation, let's say equation that says c must be this. So what is this relation that you would apply to find the c?
Since each position at the surface, that means if you want to find the probability, it should be the surface of the position you consider over the whole surface, and c should belong to R.
Inside, no, not in all surface. We consider only square, so it's somewhere in the square.
So the condition is that it should be inside the square.
Inside the square, yes, yes. Just
nowhere.
like it was in the cartoon, nowhere else, not outside the square.
Yeah.
So the particle is somewhere in the square, but anywhere with the equally likely, any configuration of this part, any position of this particle inside the square is equally likely.
I think c should be less than 1.
Why?
Is the small area, no?
What?
Because I said c should be less than 1 because the maximum probability is 1. That means if you are inside the surface, it should be
okay. That's good. So the probability must be 1. What probability should be 1? Which probability?
The whole surface.
The whole surface. So that the particle is somewhere on the surface. Definitely it's somewhere on the surface, and then probability to find anywhere inside the surface that is 1, okay?
Is the small area, no? The differential area of...
Yes, okay.
That is the density, the probability density.
Yes.
And if you integrate the probability density, you got the probability that is 1.
Exactly. So there is, when we speak about density, is that when you double integrate, because we speak about 2-dimensional density, it should give you 1. This is called the normalization condition, okay? Probability that particle, so let me write it. Then let me write it here. So that probability that a particle is, somewhere on the square, anywhere that is in the square, okay. So that probability that x is inside 0, 1, and y is inside 0, 1 is equal the integral from 0 to 1 dx and from 0 to 1 dy of p x y, and it must be 1 because somewhere it must be, okay. And then we substitute our value c, right? So what gives me if I integrate now? C, and C is constant. What is it equal to?
C needs to be 1.
1, exactly. That is 1. Because the area, so you can take it outside the integration. C could appear just easily outside the integral, right? You don't need the inside the integral to evaluate anything. An integral, the geometrical interpretation of the integral is just the area, right? The area of the square is 1. So the integral is equal c times 1, okay? And then you want it to be equals 1. So c must be 1, right? So this c is 1, okay? Now, who knows how to express? So I choose I choose just one particular spot that I don't know. For some reason, I like this spot. Let's say here. Okay, and I call this my favorite point, x naught, y naught. Okay, and I want to express in terms of probability density that my particle is always here. It can be nowhere inside the square, but this particular point. Who knows how mathematically we express probability density of such distribution? Any ideas?
Said something about density of states. I don't remember.
Yeah, just there is one special function that I hope you would have heard of that describes a probability of particle being exactly at one point and never anywhere else. So in other words, so if I integrate this function, okay, this, let me call p of x, y, still I abused the symbol. If I integrate it anywhere, just any area, I take it here or here, that any square inside this, any little square inside this square, it gives me 0. But if I, doesn't matter how large, but if I integrate over a little square or area around this point, sorry, this special probability distribution, I'm sure that particle is there, and it will give me 1. Who knows how mathematicians and physicists call this function?
Dirac delta?
Dirac delta function.
Yeah.
Who has not heard of this? I just want to understand if this is something too much I'm asking you about. So we write it delta x minus x naught, y minus y naught. Who has, no, frankly, it's all right. If you tell me that you have not used this function in your curriculum, there's nothing, because sometimes it's considered to be an advanced concept. So everyone has seen it, right? All right. So now tell me, what is between the two distributions, the delta function and the constant? The constant is called uniform distribution, by the way. So what expresses the maximum uncertainty? The uniform or the delta function distribution? Okay. Boris, or no, Boris?
I don't understand the question.
So we were talking just early when we began our course, we've been talking about uncertainty, right? So we are going to apply statistics and probability to describe uncertainty. And now I introduced you to uniform probability distribution, or basically reminded you of these two, the uniform distribution and Dirac delta. What distribution describes a particle, a position of a particle with the largest uncertainty? Uniform or delta function between the two?
With largest uncertainty.
What?
I mean, you said with largest uncertainty.
Largest uncertainty.
Yeah, it's the uniform distribution.
Uniform distribution, right? Is that any probability distribution, in principle, has some, most of them have a probability density function that not always can have a closed form, but they all have. Okay, probability density function is a thing that I hope all of you know what it is. And it seems you are, maybe you are rusty. Then I was starting to rationalize her ideas about the uniform distribution by using standard deviation. Okay, standard deviation is a statistics. Okay, so it's a statistical quantity. So if I give you a distribution, so distribution will have, okay, distribution will have probability density. How can we else characterize it? It will have average number. It will have standard deviation, which usually defined like this. Okay, and so what I was asking, how do you calculate the average value if I give you probability density?
By the integral of the variable multiplied by the probability distribution.
Yes, so yeah, let's work in one dimension, okay? Just for simplicity, no areas, really simple problem is how to calculate the average, okay? So this has a precise definition, okay? This is X. And if I said that your probability distribution is 1 and X is only between 0 and 1, you can calculate this number, right?
Yeah, 1.5.
By the way, let me check if I normalize it well. Yeah. So this is X minus X evaluated at 1, X evaluated at 0. So, and it is 1, right? Okay.
We are having a variable X.
Yeah, okay. So now, so it is normalized. Oh, I just for self-check. Now we have dx times x from 0 to 1. This is equal x squared over 2, evaluated between 0 and 1. And this is 1/2. Okay, so now I was, I said that Gaussian has a standard deviation. So the question, does the uniform distribution has a standard deviation? And
yes, it does. It does have a standard deviation, but I don't understand the uncertainty part. That's I do not understand that.
Good question.
What are we talking about? That's what I'm saying. I'm confused.
Now I understand
what are we
your
talking
question.
about?
That's a good question. All right. So look,
I mean, I can do these calculations, but I don't get how uncertainty
So
fits into these calculations.
Yeah, so if I say to you that standard deviation of one distribution P naught, okay, is, let's say, 0.75, and P1 of another distribution, okay, this is uncertainty, okay, this is the standard deviation, okay, and another gives you standard deviation 0.5, which is most uncertain.
0.75?
7 what?
0.75?
7.5, yeah, because how do we quantify in statistics number? So you can say that your average, on average, something is equal to, let's say, plus 0.5 plus minus 0.75, okay? Is a lot of uncertainty, right? Standard deviation is used to characterize errors, right? And so standard deviation is, in fact, a measure of uncertainty. And of all the possible probability distributions, the most uncertain will be the uniform, because particle can be anywhere. You just cannot define a distribution on the square, which would give you a more precise information about position of the particle.
Okay,
yes, it's like a dispersion.
Okay. Yeah,
I would say.
Okay.
Yeah. Let's talk. It's good to talk, and sometimes I cannot understand what was your difficulty, but we should talk. Physics is actually a lot of talk to understand. Okay, then what is the entire counterpart of uniform distribution? When you have absolute information.
Delta distribution.
Delta distribution, exactly. When you just want to say that something is there and only there, you express it by delta distribution. And any other distribution that you can define in this square will be somewhere in between, all right? And the point of statistical physics is often that you have a problem, find X given this information about X. And you are trying to find X and quantify its distribution, okay, where it could be. And depending on your approach, you may find a tool that gives you better or worse uncertainty, which would be expressed formally as a probability distribution that your answer lies in that square, okay? I hope that now is clear, this point that I'm trying to make. Do you have any questions? Other questions then, except this relation between distributions? Mm-hmm. All right, just another homework. Please find the standard deviation of the uniform distribution, standard deviation of Gaussian, Gaussian, not standard deviation of delta function, and standard deviation of, let me call it, triangular distribution. Let's work in one dimension. So first question, P of X equals 1. What is the standard deviation? Sometimes actually one can use double bracket to mean, so that's variance. The standard deviation, by the way, would be a square root, okay? And second distribution is delta function, centered, let's say, at 0.5, and X is from 0 to 1. Yeah, same. Find the uncertainty, the standard deviation, and let me add this triangular distribution. 0.5. So this, so it's a triangle with equal sides, okay? So this is the probability density plot. This is X. And this is probability density, which forms this triangle with equal sides. Okay, questions? Yeah, I understand. Maybe for some of you that is very simple, but I have no other means to convince myself that you remember how to do that. Okay. All right. That's good. But now we introduced uniform distribution delta functions, and these are already distributions over continuous variables. And when we speak about continuous variables, we could call this space of all possible variables x and y, we can call a phase space. Okay, how it's spelled is phase space. So it's a way for physicists to tell, to call the space where these microscopic configurations live. Okay. Okay. However, all right. Now I turn to the question of particles. Okay. You know that statistical mechanics was first introduced, first developed as a means to describe how macroscopic theories succeed in describing collective motion of many molecules. Okay, but in classical mechanics, a particle, how do we describe a state of one particle? Okay. To completely specify a state of classical mechanics, a particle of mass m, okay? What do we need?
Hamiltonian.
Hamiltonian is actually a way to describe
positions.
dynamics. Okay, okay, yeah.
The position and velocities?
Position velocities, yeah. That's the phase space, 6 dimensions.
Yeah, exactly. So it's we have 3 physical dimensions in the world around us. Let's call it D. We have position and velocity. Okay, and these are 2 things, right? 2 independent, as we say, degrees of freedom. And there are also along each direction, along each of the 3 directions, there are 6. And then what was n is the number of particles. That's how many dimensions of the phase space we need to describe n particles, all right? So someone told about Hamiltonian. So what information do we have if someone gives us a Hamiltonian, okay? With all particles and positions. Energy, but what do we use? So if I give you some Hamiltonian that it's sum over I xi squared, for instance.
Momentum.
Yes, we need momentum. That's good. So basically, we usually call this thing in square bracket momentum. So when we speak about Hamiltonian, we actually use positions and momenta. Okay. But Hamiltonian is actually in classical physics is a way to encode dynamics. So it tells you just how things will evolve in time. However, that's right. So if we take particles and constrain them, okay, we take gas molecules in a cube, put walls around it, okay, and particles can move only around here. So what do we know? Nothing can happen from outside, nothing affects this particle. So what can we say about its Hamiltonian? How does it change?
Nothing can affect the system?
Yeah.
Now
I'm speaking about classical mechanical systems.
The total energy of the system.
Yes, it's total energy of a system that must be conserved. Yeah, it's conserved. So if I say that it's a Hamiltonian system, and Hamiltonian of I add of isolated system, so nothing externally changes anything inside, the energy of such system and the Hamiltonian that corresponds to this energy are constants. Okay. Okay. And basically, we already introduced this concept. When you have absolutely no information, there are 6n degrees of freedom, and we know that x can be just inside the cube. And I tell you that energy is conserved, and I tell you the energy, okay? So how can we express in statistics that whatever happens, but the energy of these systems is always equals E? Probability distribution of E, energy. So I know exactly, it's E.
Delta?
Delta, very good. So it is delta of H, X, P's, I mean all H, X, all X's and P's along all directions here, minus E. So delta function gives you non-zero result only when its argument is equal to 0. So when I find X and P such that they equal E, this quantity inside the brackets cancels out, and we have we found the probability density of these particular states. But now so if we consider that so it's single gas, okay? So monoatomic gas consisting of same particles, okay? What do we have to do to account that swapping two gas molecules doesn't change for us anything? So we have n particles, right? N. How do I express the fact that any permutation of this particle is the same for us?
Divided by n factorial.
Exactly, very good. So that's the trick we used earlier. You remember when we spoke about two particles in the carton, and we had to divide by n factorial because they were indistinguishable. Swapping two particles doesn't matter. So that's would be the probability density of a system with this given energy, okay? So we fixed here, all right? I iterate n, which is the number of particles, does not change. Volume, V, and energy, E. So who knows the concept that goes around with this NVE abbreviation? Okay.
Ensemble?
It is ensemble, right? Which ensemble? How do we call this ensemble? Who knows? Well, we could call it NVE ensemble, by the way, but there is a better name for that. It's a slang. So, who remembers?
Then we have the canonical, the canonical, and I forgot the...
It's called microcanonical.
Microcanonical.
It's a micro. So there is no dash. it's canonical. So okay.
Isolated systems.
Yeah. And what we used here, actually, we said that we only know about the system that it has energy. And I hope that it already comes to you naturally that we assume that one made important assumption, because we have no other information about the system. We assumed that any configuration is equally likely. Okay? It's just because we don't really have any information about the system except that it's inside this volume. There is there are n particles and a given energy. This is an important concept which is named after, is called as Boltzmann's postulate of equal probabilities, okay? And that's what forms the concept of a microcanonical ensemble. Now, the thing is that what is actually an ensemble? Okay, what then word ensemble means? Who knows?
A collection of same systems?
Yes, exactly. So usually we imagine that it's a collection of systems that live in, so imagine that it's a cube, okay? But there are like many of these things, infinitely many. And each in this collection is a particular possible configuration, okay? Just one of n particles here, then there is another one here. In reality, when we observe just one system, it's an important thing. We assume that when time evolves, okay, your system, let me change the color. So your systems, while it evolves in time, it moves particle, it passes through different states. So if you observe one system for a long time, it is assumed that you observe, it's the same as if you observed many parallel systems existing in parallel universes. Okay, this is actually called ergodic assumption. So this is ergodic hypothesis. Ergodic, oh, sorry, I think it's E. Ergodic, yeah. I hope I spelled right. Okay, so the ergodic hypothesis says that if you observe one system for a very long time and you see each of states that it passes through, it's the same as just considering the whole ensemble of systems that exist in parallel. Now, it's not all systems actually fulfill this condition. I can give you an example. So we consider this cube of particles. Suppose I have two particles, okay? And I make one particle move in the direction, okay, x, and one particle at a different coordinate z, also in the direction x. So what will happen? The particle will just bounce between the walls, and the other particle will bounce between the walls. They never cross, right? Then we never observe in this system, okay, that the particle was here and another particle was here. That will not happen, okay? That's example where ergodic hypothesis breaks. If we observe such a system, we never come to this state. So it's rather empirical fact that when you have many particles, like 1,000 with or more in a box, sufficiently small, then usually you will it will be very difficult to find such conditions that while system evolves, it will not go through all possible states. So in this system of two particles that I described, ergodic hypothesis may break, but we can consider an ensemble still. So as a concept of microcanonical ensemble, it exists. But observing a single system, we will never observe, see all configurations. But on the other hand, why do we need to describe a system of two particles with methods of statistics, right? So that's the one point that rather I tell you as a practical observation that we usually try to apply statistics when there is a very large number of particles or a large number of degrees of freedom if we don't speak of systems consisting of particles. And most of the time, we can take just a single system and observe it for a long time. And that would be equivalent to considering an ensemble of systems. Do you have questions? Any questions? Just any. All right. Well, since there are no questions, I think we are